Hi, this is Dr. S. Deepa, Professor EC Department, Panimalar Engineering College. In this video lecture, we'll be discussing about image enhancement using MATLAB. The contents are contrast stretching, image negative, histogram equalization. We'll see how to add salt and pepper noise to an image and remove that noise using smoothing filter and median filter. Also, we'll see how to blur an image and remove the blur using Wiener filter. Go to File, open a new blank M file. Let us read an image. A is equal to imread of pout.def. So to display this image, we'll have to use imshow function. Subplot 1 to 1. That is in the first window. I am going to display this particular image, imshow of A. Next, let us use a new file. B is equal to imadjust. Imadjust of A. Imadjust is the function used for adjusting the contrast of an image. Let me display this in the second window. Subplot. In the second window, I will be displaying this enhanced image, imshow of B. You can give the title here, title, original image, and here the title, enhanced image. So now when we run this, save the file. So when we run this, we see that the original image and the enhanced image are displayed. So what we see here is the original image is a low contrast image and the contrast of this original image is enhanced here, and this process is done using a concept called as contrast stretching. The function used for this is imadjust. Let us see how to determine negative of an image. Let me use the function b is equal to 255 minus a. Here 255 represents the maximum pixel value in the image. To display this, let me use the subplot function. In the second window, let me display the negative image. Also, let us see how this negative image works on a color image. For this, let me read a color image peppers.png, and d is equal to 255 minus c. Let us display this in the third window and fourth window respectively. Imshow c. C is a color image, and in the fourth window, let us display the negative of this color image. So imshow d, negative of color image. Now when we execute this, it appears like this. This is the original image and this is the negative image. We find it very clear. The black becomes white and the white becomes black here. And for the color image, the complementary colors are displayed. White is black. For yellow, the complementary color of yellow is blue, which is clearly visible. So when we say negative of a color image, it refers to the complementary colors in the color image. Next, let us see how to use histogram equalization function. pout.def. So for histogram equalization, the function used is histeq of A. So in the second window, the histogram equalized image will be displayed. Let us display the histogram of the original image and the equalized image in window 3 and 4. histogram histogram of the original image and histogram of the color image. Histogram of the enhanced image. So now when we execute this, the original image and the histogram equalized image are displayed here. We clearly see how the image is enhanced and also see the histogram. For this low contrast image, the histogram components are grouped in the center. When we spread this, the contrast of the image will increase, which is done here. Using histogram equalization, the histogram components are spread out, resulting in a contrast enhanced image. So next we'll see how to add salt and pepper noise to an image and filter it using smoothing filter and median filter. We'll also compare which one is better. So now to add salt and pepper noise, I'll be using the function imNoise of A. The type of noise is salt and pepper. So salt and pepper. And the amount of noise, the magnitude 0.1. So let me display the noisy image here. In the second window, I'll be displaying the noisy image and applying the smoothing filter. So let me define my filter function. H is equal to 1 by 9. Since I'm going to use a 3 cross 3 smoothing filter, ones of 3, 3. So this smoothing filter function is supposed to be convolved with the noisy image. So let me define a new image. C is equal to con2. So this 2 stands for two-dimensional convolution. So the noisy image is B, the filter function is H. So in the C image, we'll be having the smoothing filtered output image. So in the third window, let us display this smoothing filter output. So imShow of C. So here we'll have to convert this to unsigned integer format. So uint8 of C. Let me give the title here is smoothing filter output. In the fourth window, let us try to display the median filter output. Let me use a notation. D is equal to median filt 2 of A. So imShow of D. So title median filter output. Now we'll see. Let us run this. Yes, what we see here is the original image and a noisy image. That is, the salt and pepper noise is added. That is, the white grains are similar to salt and the black grains are similar to pepper. So it is called as salt and pepper noise. It is nothing but the bipolar impulse noise. So to this noisy image, when I apply my smoothing filter, this is the output obtained. And when I apply my median filter, this is the output obtained. So what we see here is the smoothing filter is not efficient, whereas the median filter is very efficient in removing the salt and pepper noise. So the median filter is more effective in removing the salt and pepper noise. Now let us see how to blur an image and restore it using Wiener filter. Again, I am taking cameraman image as my input image. This blurring operation involves lot of mathematical operations. Hence, the image is initially converted into double format using im2double instruction as shown here. To blur the image, a point spread function is used. PSF stands for points spread function. This point spread function is a special filter function, and the type of blur what we are going to do here is a motion blur, which is indicated here using motion, and the amount of motion what we are going to implement, and 11 tells you the degree of motion. So your PSF will be containing the filter, motion filter, which is going to blur the image. In order to implement the blurring, the original image is convolved with the PSF function, so which is done here using imFilter function. A is my image and PSF is the blurring function what we are going to use, and the type of convolution what we are going to perform here is a circular convolution, which is shown here. So the blurred image is displayed in the second window. Subplot 2, 2, 2 is used here to display the blurred image. So now we'll see how to deconvolute this using VNF filter. So when you apply a VNF filter, the format for using VNF filter is deconvolution of WNR stands for VNF. So the blurred image is my blurred image, and PSF is the filter function which we have used here already, and 0 tells you the estimated noise to signal ratio, NSR. So initially I am considering my NSR as 0. So using my NSR as 0, I am deconvoluting using the VNF filter. Again I set my NSR value as 0.001 and I perform the deconvolution operation, and both the images are displayed in third window and fourth window respectively. So now when we execute this, so this is what we get here, the original image, and here what we see is the blurred image. You can just see the amount of blur. This is the motion blur which we have simulated, and this is the restore image with NSR is equal to 0, and this is the restore image with NSR is equal to 0.001. As we increase the NSR value, what we find is the false contouring is also increasing. Thank you for listening.